Our planet is on a budget. Instead of dollar bills, the currency we'll focus on in this module is energy. And we have to understand the flow of energy into, around, and out of the Earth atmosphere system. And this is true at all scales, from why cloudy nights generally tend to be warmer than clear nights, to being able to properly think about the greenhouse effect and global warming. Now, much like your personal finances, you must account for incoming and outgoing funds. When more money comes in than goes out, well, your checking account balance climbs. When you spend more than you earn, your financial reserves dwindle. And so it is with the Earth and its energy. In this module, the first thing we're going to learn is that light is more than meets the eye. Really, our eyes are only sensitive to the visible wavelengths, which make up only a sliver of the larger electromagnetic spectrum. Now, when scientists refer to light, they mean more than just visible light. They're talking about gamma rays, and ultraviolet, infrared, microwaves, radio waves. Now, I should mention that radio waves are not to be confused with sound waves. Sound waves are not electromagnetic energy. But anyway, think about how much goes on that we don't experience directly because our eyes are rather limited measuring devices. They only pick up visible light. Thankfully, science and engineering have provided us with instruments that can detect other forms of light. In meteorology, the development of such instruments have allowed for the emergence of satellite imagery, not just visible light images, but also infrared images as important tools for weather forecasters. Now, once we've understood that light takes on many forms other than visible, we'll delve into two fundamental relationships that have to do with electromagnetic radiation. The Stefan Boltzmann law essentially says that the hotter and larger an object, the more energy it emits. For example, our sun. It's hot, about 10,000 degrees Fahrenheit at the surface, and it emits a lot of energy. In fact, enough energy to support life here on our planet, which is 93 million miles away from it. However, the sun's energy output is nothing compared to Polaris, the North Star. Polaris has about the same temperature as our sun, but it is 50 times larger in diameter than our sun and therefore produces 2,500 times as much energy. Now, Wien's law is that other relationship that we'll learn about. That has to do with the wavelength of the electromagnetic radiation that an object emits. Our sun produces all kinds of electromagnetic radiation, some UV, some infrared, etc. But its peak lies within the visible spectrum. Hotter stars tend to peak at smaller wavelengths than the visible spectrum, while cooler stars peak at longer wavelengths. And finally, we're going to learn what happens when light hits stuff. It can either be reflected, transmitted, absorbed, or scattered. Once we put all these concepts about the electromagnetic radiation in our mental banks, we can tackle the topic of Earth's energy budget and how it relates to daily and seasonal temperature trends. We'll also discuss the greenhouse effect and how it is related and unrelated to global warming.